Okay, so we're recording our vectors lessons, and we are going to be basically following this first unit learning goal. We're going to try to learn how to define, sketch, and label a vector. We should be able to put them in position vector form, and other forms. We should also be able to find magnitude, direction, and use at least 3 different notations. We will only use the first 2 notations today. Okay, our first objective is just to learn to graph a vector at the origin. That's a report, pretty easy. And any other position on a piece of graph. Okay. You should know how to label the vector's head, tail, magnitude, and direction, and to give appropriate letters and values. And you should be able to do it pretty much every try. It's really easy stuff today. Okay. In terms of difficulty, this is obviously the easiest lesson of the chapter, of the section. First thing I want you to do is use your smart device, or if you don't have one, use your textbook, and look up section 8.4. We're looking for a specific definition. What is a vector? So this is 8.4. Right in probably the very first sentence, you can just grab your book and look. Or if you have a smart device, feel free to just access the internet. Just try to fill those 3 blanks. Okay, so a vector is, and you could put any quantity that has both a magnitude and a direction. So what if you don't know what a magnitude is? Well, you just go on the internet and research that. Okay, or look it up. Magnitude in everyday language means what? What does it really mean? Length, size. Okay. Now do me another favor. Look up the word position vector. Position vector. You might get multiple definitions on this. Okay? So you're trying to get the definition that matches my sentence here, please. A position vector is any vector that has its what located at the what. A position vector turns out to be what? Any vector that has its... Did you guys find it? Anyone find it? Initial point located at the, you could probably guess this word, origin, right? Okay. Now I'd like to just take a few minutes of class time, see if you can come up with some examples of vectors. It can be anything that requires both a size and a direction. Okay? So I will start. And then you guys can brainstorm from there. One thing that always kind of needs direction attached to it is force. If Mr. Short says I'm pushing with 100 pounds, listen, if I tell you I'm pushing with 100 pounds, and I don't tell you which way I'm pushing, there's no way you can really know if the object is going to respond. For example, if I told you I was pushing on this whiteboard with 100 pounds, many things could happen. If I'm pushing this way with 100 pounds, nothing's going to happen, right? But if I'm pushing this way with 100 pounds, something might happen. The heads of the nails might shear off and the whole board might collapse to the floor, right? Or if I'm sort of behind the board somehow pushing on it with 100 pounds, it'll probably just pop right off the board, right? I'm not sure it can withstand 100 pounds. If this show's hanging on it like Tarzan, and puts his feet up in the air, that'd be 150 pounds, roughly. That might fall, right? Okay, my point is, without force, without direction, force is pretty much meaningless. Right? When somebody says, I weigh 100 pounds, well, that's a force too, but obviously they mean downward, right? You weigh 100 pounds, downward force. But force really requires direction. You can't talk about forces unless you're telling me which way you're pulling or pushing. Make sense? Okay, so my example's force, but there are many others. In high school, specifically 4 or 5 that we often use. So, can you guys brainstorm a couple? And I will pause the recording so you can just shout it out and not feel like your voice goes on the internet. So record that one. Okay, so I mentioned force. Forces need direction and amount. Speed doesn't really need it, but velocity does. Okay, so we'll write down acceleration. And also any quantities that are connected to these. For example, if you take mass times velocity, we call that momentum. Since velocity is a vector, I'm sure momentum is too, right? If you take mass times acceleration, we call that a force. Acceleration is a vector, you just multiply it by m, it's still a vector. Okay, so we'll talk a lot about vectors in this chapter, but these are the kind of top three that students know about. We also have things like momentum. We have torque, which is a different kind of force. It's a twisty force. We have angular momentum, which is twisty momentum. We've got quantities that are definitely not vectors. For example, if I say mass, right? The mass of this stapler is 1/2 kilogram. Do I need to give a direction to that? I really can't. Like, what would you say? It's 1/2 kilogram north? It doesn't make any sense to assign a direction to mass. Okay? What if I say, man, that homework took me 15 minutes. Do I need to describe a direction? Of course not. Time doesn't pass any direction. Time just passes behind the scenes, you know? So I guess you could say, well, time, it took me 15 minutes of future time. Or I could say, it will take me 15 minutes to get to the store. Obviously, I mean 15 minutes into the future. I don't mean 15 minutes into the past, right? Okay, so we don't really use time as a vector at all. Okay, so we have a few that are and some that are not. So let's write down a few non-examples. Non-vectors. We actually call them scalars. We'll talk about why later. We'll talk about it on day 3. Scalars. That's an S-C-A-L-A-R-S. Okay. Some scalars or non-vectors are time, mass, volume, although we will actually see some volumes are negative. We'll see that in this chapter. That's kind of weird. But if somebody just says volume, they're probably talking about a scalar volume. All right, so anyway, that's enough of that. It's kind of fun to talk about. Okay, let's go to our next section. On this section, we're going to draw a little bit. We're going to start off by drawing a vector with its tail at 2, 4 and its head at 10, -5. Okay, I'm sure you could probably sketch something for me, right? But I'm going to kind of do the first example, and you're going to have a chance to try it anyway in a minute. So 2, 4, that's obviously this point, and 10, -5, it's right here. And we'd like to draw a nice straight line between them. In fact, it's supposed to be like an arrow, it says. It says sketch an arrow vector, so I guess vectors look like arrows. Okay, it says that the first point is called P, the second point is called Q. It tells us to put the tail at P and the head at Q. Obviously, the head of an arrow would be the sharp part, I guess. So I guess we're supposed to put a little head right there. That's supposed to look like an arrowhead. Okay. So I guess this is what a vector looks like. Okay, so let's talk about it for just a second. In geometry class, you learned about segment PQ, ray PQ, which is totally different. Hold on, let me erase that. So ray PQ, and we have line PQ. So these are just some old geometry things. Segment PQ looks like this. Starts at P, ends at Q, done. Ray PQ starts at P, passes through point Q, but it's not done. Keeps going forever. Line PQ basically passes through point P and Q, but they are not really endpoints. In fact, lines don't have endpoints. They just go on forever in both directions. This is a brand new object. This PQ vector thingy, this is brand new. Think of it as the 4th type of way to connect 2 points with a straight something. It's not a segment because it's got a direction. It's not a ray because it has a stopping point. And it's not a line because it has a starting point. It's new. It's brand new. Some people actually call it a directed segment. But we're going to call it a vector. It's brand Okay? So Mr. Short's not going to call it directed segment. I'll call it vector. But that's what some people call it. Okay? Alrighty. What does it ask us to do now? Let's scroll down here, see what it asks us to do next. It says, label the vector you drew in 1 with its name, PQ. Notice the symbol here. This thing is called a harpoon symbol. Harpoon. Okay? And the harpoon PQ is the name of this thing. So I'm going to actually go up here. I'm going to put a name right on the vector. Bless you. So let's go and put a name on this thing. It's harpoon PQ. Don't draw a ray arrow. Ray arrows look a little different. Right? This is the ray arrow over here. It has sort of a double top there. So let me write that again. A ray arrow looks like this on top. See? That's different. That's not a harpoon. That's an arrow. Okay, so PQ is a different symbol. You cannot call this QP. I'm sure you know why. Same reason why you can't call this ray QP. You have to call ray PQ. In the same way with vector, just be careful. Don't call it ray. Don't call it vector QP. What's the reason for that? Just for fun, you know. Okay, yes. So we will not call it QP. And the reason? QP has the opposite direction. That's what you probably want to put here. QP would point in the opposite direction. And the tail would be at Q. Head at P. That's totally different drawing. Okay, it says to write the 2 components of the vector. Okay, so I'll just help you fill that in. So the 2 components of the vector is talking about, imagine trying to travel from point P to point Q using just rectilinear motion. So just rights, lefts, ups, downs. You would have to travel to the right far enough to go from x equals 2 to x equals 10. So how far to the right would you be traveling? 8. So it's right 8. And then you'd have to travel on the y from up here at 4 to get down here to negative 5. So how far down would you have to travel? Down 9, right. So basically you'd write down 9 here. If we use the traditional convention that down is a negative, we could call this vector the 8, negative 9 vector. The 8, negative 9 vector. So that's what we'll put in the brackets here. 8 and a negative 9. Notice the brackets are diagonally bracketed. This is a brand new symbol also. It just is pronounced vector PQ. This is called the rectangular component form. Rectangular components. And this little guy, of course, would be called the x component. And this little guy, you guessed it, he's the y component. X component, y component, obviously. Okay. We could find the length of the arrow, the vector. We could find the length of the vector. So let's go back up and take a peek at our vector again. Couldn't we use the Pythagorean theorem to find out how long the blue segment is? The blue directed segment? I think we could, right? So do me a favor, calculate the length of this thing real quick. Let's put it in radical form and decimal form real quick. Square root of what? Okay, so what's 64 plus 81? 145. And if you type that into your calculator, you get 12.042, right? I think I remember from earlier today. Okay, so remember when we did complex numbers, this was called the modulus. This is now called the magnitude. But it's the same thing we've always done, just x squared plus y squared square root. Okay, so it's now called magnitude. And notice the double, look at these interesting symbols. You've got these double absolute values there. Kind of cool. Okay, that's how you pronounce it. You pronounce it magnitude. Magnitude of vector PQ. So the magnitude of vector PQ is exactly root 145. Which is approximately 12.042. Okay, find the direction of vector PQ. I don't mean right and down. I'd like an actual angle. So we've done this before. Do it the same way you did when you put a complex number in polar form. When you put a complex number in polar form. So remember how you did that? You did arctan y over x. Right? So do that. Arctan y over x. Might need a calculator for that. When I did arctan y over x, I got negative 48. But I added 360 to that because Mr. Short doesn't like to have negative angles when he does complex numbers and vectors. So 311.634. 311.64. So how did I do that? I just basically did arctan and then negative 9 over 8. Okay, so 311. And usually we'll just use 3 digits after each decimal because you guys need to be ready for the AP exam next year, and they always ask for that. So it was 0.634. There we go. Okay, notice that adjacent should always be hypotenuse times cosine. Opposite should always be hypotenuse times sine. So we could actually write our x component like this. 12.042 cos 311.634. Oops. And we could write our y component as 12.042 sine 311.634. This is sort of decimals in the wrong spot. There we go. In other words, we could actually write our vector like that. I didn't really leave you enough space here. Sorry about that. Mr. Short's going to give himself a little more space. Need to put in those two components in this little bracket. So you'll have to write small or just rewrite it. Sorry about that. So anyway, I'm going to put in 12.042 cosine 311.634. And then we have 12.042 sine 311.634. Okay, tomorrow we'll talk about why we're allowed to pull up 12.042. So we could write that in the front. Okay, so I'm going to write that one more time. This is my final rewrite of vector PQ. I'm going to put the 12.042 in the front. Then I'm going to put a cosine 311.634 comma sine 311.634. Man, this should feel really, really, really familiar to you. When we did, remember we took we took a comma b, or sorry, a plus bi, and we changed it to r cis theta? It's pretty much exactly the same thing. We used to put our modulus out front, and then we would write CIS. The only difference now is there's no I, because it's not imaginary, and we're not using plus, we're using a comma right here. It's basically the same amount of work and difficulty as complex number conversion. So let's title some things real quick. I would call this, if I had to give this a name, I would call this polar component form. what I'm going to call it, polar component form. And then up above, that 8, negative 9, I would call this rectangular component form. I already wrote that, yeah. I'll write it one more time. Rectangular component form. Okay, so we have rectangular component form, that's 8, negative 9. Polar component form, that's the 12.042, blah, blah, blah. In the homework in our book, they just say it this way. Please write the vector in terms of its magnitude and its direction. Please write the vector in terms of its magnitude and its direction. Okay, but I'll just call it polar component. Okay, so not really anything new in terms of how difficult it is, but here's something new. It says, now move your vector, so this is on the back, then flip over. Move your vector from where it is so that its tail is at the origin and rename it u. Okay, that's kind of interesting. So we would never do this with a complex number, but what we're being asked to do is to move the vector so its tail is at the origin. Get my page here. Scrolling slowly today. Okay. I think they're asking us to put the tail at the origin. So that's kind of where you put point P. And then since it's right 8 down 9, we'll just find the point 8, negative 9. I'm sorry, since it's, yeah, it'd be the point 8, negative 9. So this just sort of drew that in the wrong spot. Hold on. Erase some of this scribble, scratchy work here. Okay, yeah, so 8, negative 9 would be this point. So I just basically redrew the vector so it's no longer over at 2, 4. It's now starting at 0, 0. Okay, a couple things you need to know. This vector is completely equivalent to vector PQ. It has the same length. It is the exact same direction. The only difference is it has a new name, u. Okay? But it's technically the same vector in every other way. In fact, now that it's called u, you can even move it elsewhere and call it u. So like you could actually put it like you could shift it 2 spaces left and a space upward, like this, as long as you move both head and tail. And you can still call it vector u. So I'm not changing its name because I'm moving it. I'm changing its name because it doesn't start at P and at Q anymore. P and Q are fixed points on the grid, but this vector u now can be moved anywhere you want, and it can always be called u from now on. What do we call it when it's at the origin? Yeah, so that was the second thing I had you look up on the internet. We called it a position vector. So let's fill in some blanks here together, okay? When translating a vector, not just a figure, but when translating a vector, what must you be careful not to change? Don't change its magnitude. Like, keep it the same length. Don't change its direction. Keep it pointing the same way. Now the vector is at 0, 0. But the head is at 8, negative 9. The head is at 8. I didn't mean to have 0 there. The tail's at 0, 0. The head is at 8, negative 9. And is now called a position vector. That was our second little internet search there. Okay, now you try it on the second sheet I gave you. Basically, you're going to do everything I did. Just be careful about that angle. Be careful about that angle. A quick sketch of this will show you basically that it's pointing left and up. So it's kind of important. I think it's kind of important that you sketch something personally. That's how I feel about it. Okay, so you can plot the first point at negative 3, 0, right? and the next point at negative 6, 2. Make sure you put the head at the point K. And instead of calling it vector JK, because then it would sound like I'm joking, JK. We're not going to call it the vector JK. Let's just call it the vector V the first time. Okay, and then we can move it to the origin if we want, and it'll still be called V. And there will be no reference to start and stop. It'll just be like a run and rise. But you'll notice it goes basically left 3 and up 2. See that? It points left 3 and then up 2. So this is kind of like a run and a rise. That's an excellent way to think about it. It's run, comma, rise is what it is. Oh, okay, polar component form. So if you find the magnitude, you would basically have rad 13. And for the angle, you can't trust that calculator. Why not? How come you can't trust it? Okay, so yes, we're going to add 180 when the calculator lies to us. So, okay, so let's see. The calculator, what did the calculator say? When you do inverse tan 2 over negative 3, the calculator says what? Negative 30 what? Yeah, I'll just round it this time. I'm not really supposed to, but I'll just round to negative 33. That's a lie. There's no way. That's right. How could that be negative 33 degrees? That's like 150-ish, right? That's impossible. So you're going to add 180. The calculator doesn't know this, but you do. You should have gotten 146 point something. Okay. So this should be a 146 point something. Might be closer to 147. I can't remember. But that's how you'd write it. Why did we have to add that 180? So we had to add 180, but why does this issue arise? Yeah, the x component was negative. So we've seen that before. At least it's consistent with the rules of complex numbers. So give a general rule. You will add 180 if and only if, so we write IFF in math. If and only if the x component is negative. Okay, let's draw it at the origin, and then we'll still call it V. So draw it at the origin and still call it V. So it's going to look like this. Just real quick, just for kicks, do me a favor. Let's take the U from my first example and the V from your example. Remember, my U was 8, negative 9, and your V was negative 3, 2. See if you can figure out how to add those and draw it. See if you can come up with any interesting observations. It's really tomorrow's lesson, but I thought it'd be kind of fun to see if you notice anything cool. You guys have a worksheet tonight. Does anyone want a hard copy? Okay, I'll print that out for you.